All right, let's do some illustrations of the impulse momentum theorem and how to use it to solve problems. As a reminder, we derived in the last thing that the change in momentum during some process is going to equal the impulse delivered during that process. So we have two different things, and we can compare their calculations to try and get new information. A force pushes the cart for 1 second starting from rest. To achieve the same speed with a force half as big, the force would need to push for how long? All right, well, since we're starting from rest, and then we want to reach the same speed, we want the same final momentum, which means the same J, but J is F delta T. So if I have halved F, I must double T. It must take 2 seconds. Remember that momentum and impulse are vectors, so it can be as simple as saying something pushing along one direction and everything's nice and easy to compute, or it could be more complicated. For instance, a soccer player getting hit by a soccer ball and hitting it not along its path of flight but at some angle. By imparting some impulse via, well, ouch, the head, the thing goes off with some other momentum, and it's got to be that they form this sort of triangle that Pi plus J equals Pf, because as highlight here, this is the same as saying delta P equals Pf minus Pi, which of course it is. That's what delta means, and J equals that. So we can solve over and get a generally useful thing to know. The final momentum is whatever you started with plus how much it changed, which is sort of duh. Right. A puck, seen from above, was moving with initial momentum when it received an impulse J from a hockey stick, giving it the final momentum shown. The J is also shown. Which arrow best represents the puck's initial momentum? So we don't have, out here, we don't know where that should be. But we do know that when we add this to whatever we had, we get this. Actually, by looking at the last one, we can short circuit this. We could go through saying, oh, well, from our earlier formula, since delta P equals Pf minus Pi, and that equals J, we could do something like saying Pi equals Pf minus J. But here, we don't have to do that kind of work. We end up with a momentum that has some upward component. Some part of P points that way, but no part of J points that way. So the initial momentum had to also have a thing pointing upward somehow, and then other stuff. And there's only one that does that, so it must be that guy. What impulse in Newton seconds is delivered by this wall, using plus x as rightward? Here we just compute J is delta P, and we end up that we're moving rightward at the start, so we have plus 1 here. Sorry, moving rightward at the end, so we have plus 1 here. We were moving leftward, so it was a minus sign, but then we get this minus sign from the delta. So we really end up having 10 minus 20, or 30 kilogram meters per second, which, by the way, is 30 Newton seconds, since those are the same thing. A 2 kilogram object moving to the right with speed half a meter per second experiences the force as shown. What's the object's speed and direction after the force ends? Give that a go. Here we're going to use that this area is J, which means it's also delta P. So we have Pf is Pi plus delta P, or Vf is mvi plus delta P all over m. To see that calculation a little bit neater, we continue here and we just do some algebra. We find out that it ends up at 1 meter per second, and because of the implicit plus, it's also to the right. What is the impulse in kilogram meters per second delivered by the ball, or delivered, sorry, to the ball by the force? Here we're going to say, well, the impulse is the change in momentum, so we take mv final minus mv initial, but we have to be really careful because here we already have a negative because we're moving that way after, and we subtract off what is a positive because we were moving this way before. So we end up with an impulse which is minus 0.6 Newton seconds, which at least is the correct direction because clearly the force has to push leftward. Half-meter hockey puck slides to the right at 10 meters per second. It's hit with a hockey stick that exerts the force shown. What is the approximate final speed? All right, well, we're going to use again that P final is P initial plus delta P, which is P initial plus delta plus J. But now we have that J is the area of this thing, which is really quite annoying because it's not easy to find that area, especially since we don't have the functional form, and even if we did have the functional form, we'd have to use calculus to do it, and that's no good. So we need to make an approximation. I'm going to choose to do this approximation, which is that it's basically constant. That's pretty terrible, but it's quick and dirty, and it would be an overestimate. Or you might have a better, you might do better, I guess, if we did this. So maybe we do that one instead. So now J is that area of that triangle, which is roughly 1/2 50 newtons times 20 milliseconds, which turns out to be just about 1/2 Newton seconds. Yeah, something like that. Because remember, you got to convert the milliseconds over as well. So we get something like 1/2. Well, then our final velocity, back over here, the final velocity is the initial velocity plus J over m. We've done that in an earlier problem. So we get 10 meters per second plus 1/2 Newton seconds over 1/2 kilogram, or 11 meters per second as our final speed. So a light plastic cart and a heavy steel cart are both pushed with the same force for 1 second, starting from rest. After the force is removed, the momentum of the plastic cart compares how to that of the steel cart. Is it greater, is it equal to, or less than? Let's get the important stuff out. Starting from rest. What does that mean? No initial momentum. Both pushed with the same force for the same time. What does that mean? Same impulse. So since the final momentum is the initial momentum plus J, and we started with the same initial and the same J, we'd better get the same final momentum.